Welcome to this video on single carrier system basics. We'll explore how QAM modulation turns digital bits into signals that can travel through a wireless channel and how the receiver processes those signals to recover the transmitted data. Finally, we'll bring it all together with a MATLAB simulation showing the complete signal chain. In the digital modulation series, we explained in detail how different modulation techniques, including QAM, embed information into waveforms. Let's quickly recap the key ideas. A digital modulator takes a stream of bits and shapes a carrier wave. The carrier's amplitude and phase can be varied to represent information, and this is exactly what QAM does. To map bits into specific amplitude and phase values, we use a codebook known as a Constellation Diagram. It's a two-dimensional plot where each point represents one possible signal state. The horizontal axis corresponds to the in-phase I component and the vertical axis to the quadrature Q component. Each point in the constellation represents a unique combination of amplitude and phase, and therefore a unique group of bits. For example, 4 QAM carries 2 bits per symbol, 16 QAM carries 4 bits, and 64 QAM carries 6 bits. In modern systems, we don't manually change amplitude and phase for each state. Instead, we generate 2 separate signals: the I component, which modulates a cosine carrier, and the Q component, which modulates a negative sine carrier. When these two are added together, they form the modulated waveform, identical to what we'd get by directly adjusting amplitude and phase, but much easier to implement in hardware and software. The modulated signal is then transmitted through the wireless channel and captured by the receiving antenna. The receiver's job is to reverse the modulation process, so to extract the I and Q components, reconstruct the symbols, and finally recover the original bits. In this video, we'll keep things simple and use an additive white Gaussian noise channel, which introduces only random noise and slightly distorts the constellation points. However, in future videos, we'll explore more realistic channel effects and show how advanced receiver techniques can mitigate them. Now let's look at the receiver and see how it converts the recorded signal samples back into complex QAM symbols. The received signal is first split into 2 parallel paths. Just like in the transmitter, one path is multiplied by a cosine carrier to extract the in-phase component, and the other is multiplied by a negative sine carrier to obtain the quadrature component. These 2 signals are then combined to form the complex baseband representation of the received waveform. However, this process also generates high-frequency terms that don't carry useful information. To remove them, the receiver applies a low-pass filter, leaving only the desired baseband signal. After filtering, the receiver samples the I and Q components to obtain the QAM symbols, which can then be demodulated back into bits using the same constellation codebook as the transmitter. For those who want to understand this process more deeply, let's look at the mathematical foundation behind it. The key idea relies on the 2 trigonometric identities shown on the slide. Let's start with the in-phase component. The received signal can be expressed as a cosine wave at the carrier frequency, whose amplitude and phase vary over time according to the transmitted QAM symbols. In the receiver, this signal is multiplied by a cosine carrier in the first path. Using identity 1, this multiplication can be written as the sum of 2 terms. The first term represents the baseband component, which gives us the in-phase value. The second term is a high-frequency component at twice the carrier frequency. A similar process happens in the quadrature path, where the signal is multiplied by a negative sine carrier. Using identity 2, we again get a baseband term representing quadrature value and a high-frequency term that we don't need. Since only the baseband I and Q components carry the actual symbol information, the receiver applies a low-pass filter to remove those unwanted high-frequency parts, leaving clean I and Q signals ready for symbol detection. Now let's move on to the next part of this video and put what we've learned into practice with a MATLAB simulation of QAM transmission. The full script is also available through the link in the description. We'll start by defining the simulation parameters. First, we set the modulation order to 16, which means we're working with 16 QAM. Next, we generate the transmitted data payload, a text string beginning with Waveform Academy, followed by a sequence of randomly chosen characters. In the next step, we modulate this data using QAM. We begin by converting the text into a bit stream using a helper function. Then, we calculate the number of bits per symbol, which for 16 QAM is 4. By dividing the total number of bits by 4, we get the number of symbols to be transmitted. Finally, we use QAM Modulator function to map the bits into complex symbols using gray coding, ensuring that adjacent constellation points differ by only 1 bit. For a detailed explanation of this function, see our dedicated video. We visualize the result on a constellation diagram. As expected, we see 16 distinct points representing all possible symbol states of the 16 QAM modulation. Now let's move on to the next section, where we'll modulate the carrier wave using our QAM symbols. First, we define 2 new parameters: the sampling frequency, set to 1000 Hz, and the carrier frequency, set to 100 Hz. Next, we create a time vector. We will use a symbol rate of 1 symbol per second, so the time vector spans 1 second for each symbol. We then define 2 carrier components, a cosine and a negative sine, both generated using the carrier frequency and time vector. Before performing modulation, we need to adjust the symbol length so that each QAM symbol matches 1 second of the time vector. To do this, each symbol is repeated 1000 times. Finally, we create the transmitted waveform by multiplying the real part of the symbols with the cosine carrier and the imaginary part with the negative sine carrier, then summing them together. Let's plot the results to inspect the transmitted signal. In the figure, we can see the first 100 samples of the waveform in the time domain, as well as its frequency spectrum. As expected, 2 distinct peaks appear at plus or minus 100 Hz, corresponding to our carrier frequency. In the next step, we transmit the signal through an additive white Gaussian noise channel using MATLAB's AWGN function. We set the signal-to-noise ratio to 10 decibels, which introduces a small amount of noise to the transmitted waveform. Next, we downconvert the received signal by multiplying it separately with the 2 carrier components, the cosine and the negative sine. We also include a multiplication factor of 2 to compensate for the fact that half of the signal's energy lies in the high-frequency term that will later be filtered out. We then combine the in-phase and quadrature parts to form the received baseband signal and plot its spectrum. As you can see, the baseband signal contains 2 components, one centered around 0 frequency, which is the desired signal, and another at twice the carrier frequency, which will be removed by filtering in the next step. In this section, we first create a low-pass filter using MATLAB's FIR1 function, which takes the number of filter taps and the normalized cutoff frequency as parameters. We then apply this filter to the baseband signal and plot the spectrum of the filtered result. As shown in the plot, only the desired baseband component remains, while the high-frequency term has been effectively removed by the filter. Next, we decimate the signal to recover the transmitted symbols. Since each symbol spans 1000 samples, we keep only the middle one to form the received symbols vector. We then plot the resulting constellation diagram. As you can see, the 16 QAM constellation is clearly visible, with slight distortions caused by the channeled noise. In the final step, we demodulate the received symbols using MATLAB's QAM Demodulator function. We then compare the transmitted and received bit sequences to calculate the number of errors and the bit error rate. Finally, we convert the recovered bits back into text using a helper function and display the result. As shown in the console output, the BER is very low, so the beginning of the transmitted and received messages matches perfectly. And that's it for this video. If you'd like to dive deeper into advanced single-carrier system building blocks, check out the next video in the series on the root-raised cosine filter. Thanks for watching.